Delta difference, small but finite. Problem solving, an elegant approach. The problem. Determine the resistance between the points A and B of the frame formed by 9 identical wires of resistance R. The figure is given here. This is a problem from Krotov, a popular book for Olympiad level problems. And in physics, since most of the times we go from the first principles at +2 level, the problems are not actually lengthy. The idea is to test their understanding of the first principles. The problems are not deliberately made lengthy. But sometimes in certain areas like this, the problems become lengthier if you do the conventional way. I'll show you the solution given in the book Krotov. The solution figure is shown here, this side. Of course, the heading of the video was symmetry and node analysis. Even in Krotov, the symmetry idea is used, but loop analysis was adopted. Look, Kirchhoff's rules, or the Kirchhoff's rules as it is called, they are basically derived from the basic principles of physics. The principle of conservation of energy and the principle of conservation of charge. The junction rule, currents entering a junction is equal to sum of the currents leaving the junction, is based upon charge conservation, and in a closed loop, sum of the potential differences is 0 is based upon the principle of conservation of energy. The second rule generally will be referred to as loop theorem or loop rule. The first one is generally referred to as junction rule. So in Krotov also, the symmetry idea of the circuit is used. I will just talk about that a little while later. But here, the currents were taken so that you could apply Kirchhoff's second rule for different loops. But look, there are 5 currents in all. Of course, even the 5 currents are achieved here by taking the symmetry. Look at this currents, I1 this side, I2, and then say I3, I5, and I4 here. So there are in all 5 currents. So 5 simultaneous equations were written, and 5 equations have to be solved. Generally, when you see 3 only, you will feel threatened. Or should I solve these 3 equations? 2 is all right. But 5 means definitely you will be put off. We'll apply the ideas of symmetries here as well, but we'll go for the node analysis. What is node analysis? You recognize the potentials at different points. Look at this circuit. Between A and B, we need to find out the equivalent resistance or the effective resistance. So as the current enters A and goes out of B, potentials and currents will be changing across the circuit. So this node analysis involves recognizing potentials at different points and applying junction rule basically. And this method will be a powerful tool, especially when there is symmetry and you're asked to find out effective resistance between 2 points. If there are many cells and branches, a combination of loop theorem and junction theorem we apply. But in this particular type of problems where a big circuit will be given but some symmetry will be given and you'll be asked to find out the equivalent resistance, this node analysis along with symmetry becomes very, very powerful. Now, what is the symmetry here? Of course, to make the figure look good, easy for understanding, we are writing it like this. And these points, let me put A and B here. This is A and B. Between A and B, we need to find out the effective resistance. First of all, what is symmetry? Look, symmetry is a very simple idea, but at the same time very difficult to understand. But as far as circuit is concerned, let us look at it. Simply flip this circuit. Flip it from right to left. If supposing I did not put this A and B here, you wouldn't even know that the circuit is flipped. Of course, if this middle one was not there, it will be a perfect symmetrical circuit. If I flipped it from right to left when you did not see it, when you came back and saw, you wouldn't even know that I flipped the circuit. That is the basic meaning of symmetry anytime. But now let us have this resistance as well. But in spite of it, we can check the symmetry for the circuit in a slightly different way here. You will think that you connected one cell between the points A and B, because that's what you mean by finding out the effective resistance, isn't it so? Like if all the circuit is replaced by single resistance, how much current it would draw from the battery as if the total circuit were existing. So now you think current comes out of the conventional current comes out of the plus of the battery like this. It will divide. Of course, it won't divide in this case equally. Like if I did not have this at all, I told you it was a perfect symmetry, because exactly from that side and this side everything looks similar. In that case, I could have told current divides equally into these two branches, here and here. Now I cannot say they are dividing equally, but whatever division I do from this side will be valid if I just reverse my poles of the battery. If I put plus here and minus here, if the current is entering like this, I would exactly divide that way. And then from there division into other resistance also will be similar when you come from this side or when you come dividing the current from the other side. So that is what you mean by symmetry in a circuit. And you can also look for the symmetrical paths. What are symmetrical paths? You start from the entry point of the current, go to the exit point, walk along identical branches with equal resistances. Then you can call them symmetrical paths, and you can divide potentials equally along those paths. Here, of course, we don't have symmetrical paths. I'll just elaborate that in the next figure. Now let me say, now once you think there's a symmetry, that means whether you divide the current from this side or that side, it is looking same, then you require to put the potentials I told you. One way to put the potentials is here, you will put plus V and 0. And then this is an equipotential wire here. You will put plus V here, 0 there. And then you go on dividing, you go on dropping potentials as you go from V to 0. Like this may be some plus V1, this may be some plus V2, this may be some plus V3, this may be some plus V4, and then after recognizing potentials like this, you will apply the junction rule. But even now there are how many variables? 1, 2, 3, 5 variables you've got once again. So the thing is not going to be different from what you do from the loop theorem. Instead of taking plus V and 0, where the number of variables have become more, we'll consider taking plus V and minus V. Remember, what we're interested is the potential difference, not the absolute potentials at a point. So whether you take plus V, minus V, or plus V 0, that wouldn't really matter. Now if this is plus V, this will be at plus V, this point A. This will be at minus V. This is point B. Now when you go from V this way, we can think that it is dropping to some plus V1, because currents are as a whole going from A towards B. So this V will be greater than V1, so plus V1. And you cannot write plus V1 here. You should be careful here, because as I told you, if the middle resistance had been not there, we would have done that. plus V1 this side, but since it is there here, the symmetry is, for that matter, for the paths violated there. As a whole, from left to right it is there, but now I cannot write plus V1 here. You can look at, like when current comes here, the way it is dividing here, the way it is connected to 2 here, whereas it's connected to 3 here, so they are not symmetrical points. Okay, so I won't be writing plus V1 here, I'll be writing plus V2. But now we think that you are coming from B side. So if this is plus V1, a corresponding symmetrical point will be this side, minus V1, and corresponding point for this plus V2 will be this side, minus V2. This is what you mean by symmetry in circuits. Now at A, let us write the junction rule. At A, I'll write the junction rule. Current is entering from here, and this is plus V, this is minus V. So the potential difference will be plus V minus of minus V, 2V, isn't it so? By R effective. That means the whole circuit's resistance is considered as R effective. That is the one which is deciding the current which will come out of the plus of the battery, that is I, equals. Now currents are dividing. Say I can put some point C, point D here into AC and AD. This is D. This point is D. So I'll write V minus V1 by R. R is the resistance of each wire, plus now V minus V2 by R. Let us call it first equation. We require 3 equations here to look at it. There will be 3 unknowns. Alright, so RE, that we wrote. Now one more point here I'll consider. The currents are leaving like this, entering like this and leaving like that. So in that case, the second equation would be V minus V1 by R is equal to V1 minus V2 by R. You can see there in the circuit, plus V1 minus of minus V2, that is V1 plus V2 by R. V1 minus of minus V2, V1 minus V2. This current and this current I considered. This is the equation 2. Now the equation 3 will be, somewhere else we should write one more relation, independent relation one should get. I'll write at this junction. Currents are entering 2 currents and 2 currents are leaving. Isn't it so? So I can write V minus V2 by R, that is the current in this branch, and V1 minus V2 by R, 2 currents entering and 2 currents leaving. V2 minus of minus V2, 2V2 by R, plus, look what is the current here, yeah, V2 minus of minus V1, that is V2 plus V1 by R. Let me check once again whether it is written right. V minus V2 by R, yes, this current, and then V1 minus V2 by R, this current is taken care, this current is taken care, that's dividing into these 2, that is V2 minus of minus V2, 2V2 by R, and V2 minus of minus V1, V2 plus V1 by R. So 3 equations have come. When you solve them, even 3 equations solving is slightly linear, but still two equations have got become less from the previous one to this. That's what I mean by smart solution. And the smart solution is not coming out of any out of the box thinking, or let me say from tricks here. It has come once again from the same Kirchhoff laws, but only thing is we are using the idea of symmetry and putting potentials instead of drawing current, taking currents and making the equations 5, now 5 there, but instead here we are able to do with 3 equations. If you solve these 3 equations, R effective will come out to be 15R by 11. That is simple manipulation which I need not have to do here. Thank you.